Welcome everyone to our interactive panel where we are looking at artificial intelligence in mathematics education. We're going to have three speakers. Each of us is going to talk for around 10 to 15 minutes. And there will be time for Q&A after each talk, and then if we need it at the end as well. All right, so I'm going to go first, and then my colleague Andrew's going to go second, and Katie's going to go third. So I will get right into it. So I'm Candace Walkington. I'm a professor of mathematics education and learning sciences at Southern Methodist University. I'm going to be talking about using generative AI to personalize mathematics to students' interests. So some background, recent advances in artificial intelligence offer really unprecedented opportunities to personalize instruction to students' interests. And when we're looking at math specifically, students interact with math in rich and authentic ways in their everyday life as they play video games or watch sports or cook or engage in a variety of other popular culture activities. So they're using math in their everyday life, but it's logistically difficult to bring that math into the classroom. So this is something that generative AI can help with. And in the study I'm going to talk about, we're going to look at how generative AI can assist students in posing personalized math problems about their interests. So another way generative AI could be used is it could be used for teachers to write math problems for their students about their students' interests. But a lot of our work looks at what if students were writing the problems themselves. So generative AI has this really rich knowledge of popular culture from the internet. And it can easily craft different kinds of math story problems, especially the more recent versions that have gotten better at mathematics. And this is something the kids generated to go with their math story problem, a bubble tea shop on Mars, using generative AI. So our theoretical framework, we're really interested in mathematical problem posing, where students generate new mathematical problems. Meta-analyses have suggested that problem posing is an important practice in mathematics education that can have beneficial effects for students. Allowing students to pose their own math problems can convey autonomy and control and can foster positive emotional responses to mathematics. But for obvious reasons, very little research has examined the potential of generative AI to support students' problem posing. So we were looking, our research question was, what are the affordances and constraints of generative AI, specifically ChatGPT and DALL-E 2, for allowing students to successfully pose mathematics story problems? So our methods, we worked with 36 girls ages 12 to 14 who posed problems using these generative AI tools in groups of 3 to 5. They were recruited from a summer camp for girls from historically marginalized communities. They participated in 5 days where they used AI to help them design an idea for a math video game. And at the end of the 5 days, they pitched their video game to a local video game company. So the data sources that we analyze here are the slide presentations from the girls' final pitches and the logs of their interactions with ChatGPT and DALL-E 2. And at the bottom, you can see an example of one of the slides from one group's final pitch, where they kind of talked about how they use AI. Okay, so we first look at the affordances of generative AI, and we found 3 major themes for the affordances emerged. First, generative AI allowed for the efficient posing and solving of story problems. Second, generative AI allowed for a match of story problems and images to very particular real-world topics and themes and particular math concepts, things that would have been really difficult to connect just on your own. And I'm going to go more into each of these. And then we also found that students use prompt engineering to refine their posed problems. This is another little slide from the girls' presentations where they actually identified these affordances themselves when they were pitching their final game and describing how they used AI. Okay, so our first theme is that it allowed for efficient posing and solving of story problems. So you can see here, one of the teams asked, make a zombie apocalypse themed probability word problem with one event in under 3 sentences. And ChatGPT is able to do it and creates a sensible problem. And then the girls ask, can you explain how to solve it? And then ChatGPT gives this nice explanation of how to solve it. They later make the illustration here for their game, which is called Dice of the Dead. It's about zombie apocalypse and probability. So you can see like ChatGPT can bring these mathematical and real world things together very efficiently while also being able to provide mathematical explanations. Okay, so our second theme, AI could bring together specific real-world topics of the students' interests, like a zombie apocalypse or robots taking over the world or a forest of fairies or pirates guarding treasure, and connect it to specific concepts from secondary mathematics that the girls were confronting in their math classes, like the probability of compound events, the midpoint formula, or factoring polynomials. So the left was a group doing problems about witches, and you'll see they connected it to midpoint where they had to unlock the crystal's true power. On the right was about factoring polynomials, which is a really hard thing to teach in an interesting manner. And here they connected it to robots taking over the world, where Jack is one of 5 remaining humans. So the third theme was the girls' use of prompt engineering. So they had a lot of these exchanges with ChatGPT where they asked it to modify the problem it was solving in various ways. Here they asked to make it harder, but then they're like, this is actually impossible to solve. It doesn't include all the information I need. And then ChatGPT actually responds and does a problem that is solvable. And then they ask how to solve it. And they go on, they ask to make it shorter. The girls would ask if ChatGPT can make the problem more exciting or insert more drama into the problem. So they used a lot of different prompt engineering on both the mathematical elements of the problems as well as like the everyday kind of interest catchiness portions of the problem. Okay, so those were some of the affordances of generative AI. We also noticed some different constraints. So the first constraint was issues of bias. The second was limitations with rendering mathematical diagrams and notations. And the third was, as you probably saw from these past slides, the math connections were often somewhat shallow. And this is an example of an illustration that DALL-E 2 generated for one of the girls' problems about a park that was a triangle. Okay, so most of the girls observed that most of the images of people that DALL-E 2 generated had light skin, despite the girls in the camp being almost exclusively girls of color. So here's a few examples. And then at the bottom is a snippet from one of the girls' slides. When we prompted DALL-E 2 to create the avatars for the game, it only generated white men and white women with brown hair. So this is something they definitely picked up on. And then they would use prompt engineering to try to overcome it and get more diverse representation of the people that were depicted. The second theme, and this one really came up a lot, is that, and we hadn't exactly expected it, we found that the girls wanted to use DALL-E 2 to make mathematical diagrams. And we had really encouraged use of it just to illustrate the story problem or illustrate their video game they were designing, like the larger concept of it, rather than to actually like map out a diagram for a problem. So there were a couple of different issues. So on the left, the prompt that the girls gave was draw a picture that shows a girl buying 25 bottles of perfume. And the picture does not show 25 bottles of perfume. So it was not able to like take precise mathematical instructions to make accurate diagrams, which if you're going to be giving someone mathematical content, you really have to think like, okay, this story says half. Does the diagram actually look like half? Or this story says there are 38. Does the diagram actually contain 38? So DALL-E 2, at least with the way the girls were prompting, wasn't responding with this level of precision. And then, for like less artistic and more mathematical diagrams, it kind of even went more downhill from there. So if the girls just asked it to draw a picture to illustrate the story problem, they might get kind of nonsense like this. If they specifically requested a mathematical diagram, that's this final one. They asked for a rectangle with length 2x, width 5y, and area z. I mean, that seems pretty spelled out, pretty, like unambiguous. But still, essentially what they got was nonsense. So DALL-E 2 was not an effective tool for making mathematical diagrams to go with the scenarios and game ideas that the girls were creating. So our final theme, and this was probably somewhat obvious from the prior slides, is that the mathematics was not well justified in terms of its relevance and authenticity. So generative AI could make these really fine-grained, interesting connections between particular math concepts and very specific real-world scenarios, like taking over the world, the robots taking over the world, and factoring polynomials. But the problem is the uses of mathematics reflected in this problem would be very inauthentic, very surface level. Like, why in the world would one of the last 5 remaining humans need to factor a polynomial to defeat the robots? Like, it doesn't make any sense, basically. And this is something that, humans would also have a lot of trouble making factoring polynomials relevant. So it's not that ChatGPT is that much worse at it than a human would be. This is just a larger problem with the nature of higher level mathematics in a lot of cases. And similarly, the second example talks about how a scientist stumbles upon a quadratic equation and a ghostly voice tells them to find the values of x that make the equation true. Okay, so generative AI can support students in posing their own mathematics problems, particularly if they want to write problems based on their interests or experiences. And it seems to be especially good at taking on some particular non-mathematical demands of problem posing, like generating an interspace storyline, richly illustrating a context, like getting the text and the structure of the text kind of down. And it can also consistently manage like the relatively straightforward mathematical demands. So with prompting, at least, it can pose a mathematically sound problem. It can provide an explanation for a posed problem, although the explanation might not be correct 100% of the time. So it definitely takes some critical interpretation. So it can do these surface level things well, which I think is not trivial given how much trouble students have with writing. I mean, how much trouble anyone has with writing a brand new narrative from nothing. Like, having generative AI to help you give it a first shot is really powerful. But probably similar to other areas, generative AI struggles with some of the deeper mathematical demands, like mathematical authenticity and realism. So some of the shortcomings we identified could theoretically be fixed by further prompt engineering, like the girls were able to fix the skin color. But others are going to be harder to fix with prompt engineering. You could ask ChatGPT to make the problem more authentic, but how authentic are you going to be able to make a factoring polynomials problem about robots taking over the world? Like, that space maybe doesn't even actually exist. And it seems unlikely that DALL-E 2 can make diagrams at this time, but there might be other image generating AIs that are more suited to this task. So our future direction, we're investigating how students evaluate output generated by AI tools in order to examine their critical thinking skills and their understanding through their prompt engineering. And this is my contact information. And if y'all have any questions, I can start with the one that I see in the chat. Okay, did you kind of inappropriate content for this age? Yeah, so we did specifically flag inappropriate content. And so we didn't let the girls directly interact with, oh, I'm answering the question in the chat, sorry. It says, did you encounter any instances with inappropriate content for this age? Okay, so yeah, so we didn't let the girls interact directly with ChatGPT or DALL-E 2. Their guidelines actually say you have to be 18 or older. So we had a researcher, they would send their prompt to the researcher would immediately put it into the generative AI, and the researcher would send back their the generative AI's response. So this allowed us to have an intermediate step where if something inappropriate was generated, we were able to catch it. There were not many instances, but to give an example of one instance, there was a group, they were generating a problem that was like a math problem that was in the style of Lizzo lyrics, and some of the lyrics were about like domestic violence. So we did not send that response to the students. And then lack of accuracy in the solutions. We actually didn't find this. I've heard from other people that for like traditional kind of problems in curricula, ChatGPT is like 80 to 90% accurate for a middle school curriculum. But asking how to solve the problem was not so common that we were getting lots and lots and lots of instances of this. Sometimes they would ask how to solve it, but it actually wasn't part of their task to ask how to solve it. So we never actually ran into an instance where ChatGPT gave the wrong answer. All right, I can probably take one more question, then we should move on to our next speaker. Does anyone want to throw anything in the chat? All right, so we are going to move on to Andrew Lan as our next presenter.
Awesome. Yeah, thank you, Candace. Can you see this? Let me make sure that I go to share screen, full screen mode. Hang on just a second. Does this work now? Is it in full screen mode? Cool. Yeah. All right. Thank you. Thank you, Candace. So my talk is going to be, both. Let me make sure I start a timer because I may go over time. Yeah. So my talk is both going to be in a similar direction as Candace's, and also on a different direction, because what we're looking at in this particular work I want to share with everyone today is about trying to look at automated distractor and feedback generation for math multiple choice questions. So it's kind of similar to what Candace has been doing in terms of question generation, although here we're looking more at the distractors and also the corresponding feedback messages in multiple choice questions. And also different because so Candace's work interacts directly with learners, but in our case, we were designing this tool in a more motivated by using it to help teachers or content designers. So this is a collaboration with a group in the UK called EDI, which is a very nice collaborator who shared a bunch of data with us. So multiple choice questions, this is probably the most common assessment format that you'll see in today's education. And then, so I'm just going to start with a bunch of terminologies that we're going to use throughout this talk. So for each multiple choice question, we have a question stem, which is just a statement of the question, including backgrounds and what the question is asking. And also a key, which is like one among its options, one correct answer and some optional corresponding explanations of that correct answer. And also a set of distractors. So most often we have like 3 different distractors, and that's also the case with us, but you can have possibly more than 3 or less than 3. And for each distractor option, there can be a corresponding feedback message written in text, either explaining what the error is or trying to provide concrete feedback about how do you address the error that you made if you selected that distractor. And what happens in practice is that these multiple choice questions, these distractors are usually manually designed. And at least with this company that we work for, they have a bunch of content creators and teachers. What they do is they will use their years of experience in teaching, and then they would go into a question and start to anticipate what kind of common errors would there be among students, and then errors or specific misconceptions, and then try to design distractors that correspond to them. However, why are we even interested in looking at this task or trying to automatically generate distractor? This is because of a couple of if you look at, so we took a look at the data that they shared with us, their multiple choice question database, and we found that despite these being good, there are some issues with this approach. The first of all is that in practice, not all distractors are actually really, really relevant. So for example, for the problem on the left-hand side, you have the correct answer, but then in some case, for many of these questions, there may be like one really, really relevant distractor that's really captures like the most dominant error among students. But then for the other two, what happens is sometimes the content designers don't really anticipate like another common error. Sometimes they just throw in some things that are not really likely getting selected by students. And from what ED observed is that some of these teacher design distractors get selected by less than 1% of students. So they're not really actually very, very useful. But on the other hand, you also run into this other issue, which is, for example, the problem on the right-hand side. You have more relevant distractors than you can fit in an actual problem. So here for this problem on the right-hand side, you can come up with 5, 6, 7 different relevant distractors, but in practice, you can only put 3 there. So this is actually kind of these observations kind of tells us that, the current format of coming up with distractors and this format is kind of a little bit is quite limiting. And another deeper issue would be that since each students have different knowledge mastery levels, so everybody has stuff that they don't necessarily master, and your weakness may not be the same as my misconceptions, which means that if we just have the same static version of the problem and the same set of distractors for everybody, then it could be that the distractors relevant to you may not necessarily be the distractor relevant to me. And ultimately, if you want to make these distractors very relevant to each individual student, one can also think of possibly even personalizing the set of distractors to make them really relevant to the individual progress. Right. So that is our ultimate goal, which is to, number one, that is a little bit beyond the scope of this work. I just want to make sure that we know where we're getting to, where we want to get to, which is to be able to automatically generate a pool of high quality distractors for each multiple choice question, and then ultimately being able to, depending on the student progress, select a set of personalized distractors. All right, but for this particular work, we're only dealing with really, really, really the easiest piece. And so we formulate 2 different tasks, automated distractor generation and feedback message generation. So we kind of treat those 2 a little bit separately. I'll explain why. And then we explore, of course, there are many ways that you can do this. You can do it manually. In some cases, very limited cases, you can use a rule-based approach. But in this situation, since we're talking about generative AI, we explore using large language models for both of these tasks. And of course, there are more complicated approaches, so stuff that we are actually currently working on. But I'm going to share something that we, in this archive paper that we put up, which is a simple in-context learning approach by giving the model a couple of examples of distractors and feedback to ask it to follow them. And then I'll also discuss a little bit about the evaluation metrics that we used, because this is evaluating is actually quite tricky. And at the end, you'll see that how challenging these tasks are, right? So to talk about both of these tasks, so we treat all of these feedback and explanation messages and also the question stem key explanations as text or math tokens. And for the distractor generation task, our goal is to generate, at least in this particular work, our goal is to generate a set of distractors given the question stem and the key, right? So given all other parts of the question, fill in the set of 3 distractors. And then for feedback generation, this task is defined a little bit differently, because you can't talk about generating a set of feedback, because feedback is specific to each distractor. So for feedback generation, our goal is to say, given the question statement and the key, given a particular distractor, I want to generate a piece of feedback message that mediates exactly that particular distractor to help students. So these are the two tasks. And our approach is actually really simple. So we just, so in this particular work, we use the Codex model because it does very, by the time that we did it, it was just a very scalable solution because it's cheap, it was free. And we use it and it does very well at math. We use a simple k-nearest neighbor approach to select 3 example questions as input because we just want to use those as demonstrations to tell the model how do you generate distractors and corresponding feedback messages. So the way we select these 3 examples would be that given a particular question that we need to generate distractors for, we go into the text embedding space, we find the 3 nearest questions. It's just a very simple approach, and then use all this information from those 3 questions, including their distractors and their feedback, and then put it into the model to let it to output the distractors and feedback for the current problem. And this is we do not fine-tune the model in any way. All right, so how do we evaluate this simple approach? So for distractor generation, we come up with, we use 3 different metrics. So these are all variants of the same version where we essentially just treat the human-generated distractors as ground truth. So we say exact, partial, and proportional match. These metrics just characterize how well does the generated set of distractors match the ones written by the humans. Here we developed another non-standard evaluation metric, which is to try to predict the portion of students that will actually select each distractor option using some data collected from ED. However, I'm not going to talk about it today because the results that I put up here is different from what we have right now. So I'm not going to talk about that. For feedback generation, of course, there's also the teacher-written ground truth feedback messages. But the problem is you don't want to really use text similarity-based metrics to evaluate these feedback messages because the 2 pieces of text are textually similar. Why? Well, would they have the same effect on students? We don't know. So we want to look at possibly using some other metrics. Of course, you can use human evaluation, but here a more scalable approach would be to use a larger separate language model, in this case GPT-4, as a simulated student. And then we basically use this approach where in the literature people commonly use it to evaluate the quality of chain of thought explanations, which is to just provide the model with the question, the distractor, and then give it the feedback message and ask it to use the feedback message to try to come up with the correct answer. And then compare this question answering accuracy versus just to asking the model to come up with the correct answer without the piece of feedback message. So that is a metric to sort of quantify how useful the feedback information actually is. Right, so we designed this, so that's our evaluation metric. But of course, this is not really perfect. So because the LLMs, we know that they really want to give you the correct answer, really sometimes ignoring the feedback or explanation. But as you'll see, this metric actually does get us somewhere. All right, so we experimented on about 2,000 multiple choice questions under a single topic related to number sense. So you see the questions are actually quite dense under the subtopic. And we unfortunately, we had to filter out questions with images. As Candace mentioned, these models are not very good at dealing with diagrams yet, so there's no way we can do that. And then here, so for the first task, distractor generation, what we see is that for these 3 evaluation metrics, so KNN does much better than random or just asking these models to do the distractor generation task. I mean, here, of course, we prompt everything in a chain of thought manner. So ask it to provide the steps and then provide the distractors. But still, you see that with the k nearest neighbors, the resulting accuracy is way higher. So so on average, 38% would be that on average, we can generate 38% of the ground truth distractors written by humans, right? So that's like a high level takeaway message. The other thing I want to say is that we also tried a bunch of different variants, and one interesting variant would be that if you just remove all the multiple choice questions from the same mathematical subtopic from the pool of examples that you can select to give to this model, then the performance drops considerably, which means that it does instead of the model really learning how the designing distractor works or how math works or all these misconception works, it's really good at picking stuff with the same topic and following similar patterns. But other than that, it's not great. Right, so for distractor, I'm just gonna skip this. So for feedback generation, so for all these qualitative examples, so we have like the paper on arXiv, so feel free to go and take a look if you're interested. And for feedback generation, we found that the human written ground truth feedback messages do beat all of these other automated methods. So they are still superior in terms of quality. But again, what we found is that although our proposed methods using k-nearest neighbors do very well in terms of these text similarity metrics, but those are not that meaningful. And surprisingly, we found that in terms of using GPT as a simulated student model to evaluate how useful the feedback message is to help students correct their answer, they don't actually do much better than zero-shot prompting. So that's kind of an interesting observation, although here the problem is that with zero-shot, we're also using GPT-4. So I think part of the reason would be that the metric likes the message, the type of language generated by itself. But for our method, because we are trying to make it scalable, we use the free version Codex, which is cheaper, and that's a different model. All right, so there are these. So I just want to kind of wrap up and talk about the limitations of our work and possible directions of future work. I would need to emphasize that this is only the first attempt to this task, and there are so many things to be done. And we are in our group, we're working on many of these different directions. So first of all, we want to really come up with a good metric about what is a good distractor and what is a good feedback message. Are there automated ways for us to evaluate these things? And that would really help in terms of model development when we are developing these methods. And also we want to be able to understand what is the exact error involved in each distractor and be able to generate distractors in a controllable way, one by one, rather than generating everything all together. And we also need to, could use these other technical approaches, but in the end, ultimately what we want is to loop teachers in to also provide their preferences on distractors, because that's valuable human feedback information. And we also want to be able to build language model-based student models as better evaluation metrics and to enable personalization, and also to run some human evaluation or possibly A/B tested this in practice. All right, so that's it. Happy to take any questions. Good. Yeah, I'm gonna quit full screen mode. Yeah, any questions? Right. Yeah. So so there's a question in the chat from Manolis. So missed how you judge quality for feedback. Yeah. So when we are evaluating the quality of feedback, what we do is we use this prompt to give a separate model, which is GPT-4. We give the model the question and the corresponding distractor as like a student selected incorrect answer. And then we give the model this feedback message and ask the model to adjust the answer using this feedback message. So then we look at how often is the model able to get to the correct answer and subtract. So that's as one value. And then the other value would be that without using any feedback message, how often does the model get the correct answer? And then we subtract the two. So that's kind of the we use that to isolate out, sort of isolate out the effectiveness of this particular piece of feedback message, right? So that's how we're judging it with the this is like an automated version of a human evaluation for sure. Yeah.
Any other questions for Andrew? No. All right, well, we can move right along to Katie's presentation.
All right. Thank you, Candace. Yeah.
Thank you.
All right, so hi there, I'm Katie Bainbridge. I'm from OpenStax and Rice University. In this presentation, I'll be describing our work using an LLM to generate metadata for math assessment questions. Having good metadata about your assessment items can give researchers and teachers really rich knowledge of student learning, their progress, and their stumbling blocks. However, manually tagging questions is time-consuming and tedious, and anytime something changes in your questions, all your tags become outdated. So here you can see an example of our manually generated metadata made with help from Candace's lab, actually. And to make this, multiple subject matter experts had to spend a whole semester manually filling out these columns. And as you might be able to guess from the column titles, one of our research questions revolves around the role that reading plays in math. One such variable that influences how reading affects math performance is question context. So questions that are contextualized in a real-world setting are more likely to use vocabulary and background knowledge that might be unfamiliar for a student and require the student to translate the problem into symbolic math, which requires greater working memory. Symbolic math questions pose much fewer challenges for students who struggle with reading. So our school math category covers questions that reference a hypothetical student solving a symbolic math problem. And they are used to assess metacognitive knowledge and are usually easier to read than real-world context problems, but harder to read than symbolic problems. And making these judgments between real-world, symbolic, and school math is relatively easy for a human, but it is tedious and time-consuming. Another category we wanted to create metadata tags for was math vocabulary. Many algebra problems use vocabulary words that can be challenging for middle school students, both math vocabulary like function and more general vocabulary like bacteria. So one day I was trudging through the manual tags for the context variable when I thought, I wonder if ChatGPT could do this. And after establishing that it was shockingly accurate, we decided to investigate whether we could use GPT to reliably replace some of the human labor used in our metadata tagging process. This would save us time and energy and would also make it possible to apply tags to larger question banks and to instantly update tags when our questions change. So to test the accuracy of GPT, we integrated it with Google Sheets so that we could sort of like click and drag it down the sheet. And then after playing with the prompts for context, we settled on a two-step approach, one that would distinguish real-world problems from symbolic problems and one that would distinguish symbolic problems from school math problems. And then we found that GPT 3.5 was actually quite accurate at generating these labels. When we looked at the errors made, the majority of them were cases of GPT coding symbolic problems as real-world problems. And almost all of these cases were graphing questions. And to give more context, we didn't actually have the graphs embedded into our question bank. So the graph that accompanied the text was not there for GPT to analyze. So this suggests that GPT 3.5 considered the graph to be a real-world context, like when given just the text of the question. And this is also pretty easy to address with prompt engineering. And this is a quick illustration of how we calculated precision and recall. The distinction didn't matter much for context because they were the same, but when we get into vocabulary, it's important to know that recall takes into account how often GPT does not identify something that the human subject matter expert did, which are false negatives. And precision takes into account how often GPT identifies something that the human subject matter expert did not. So those are false positives. We extracted the math vocabulary first with GPT 3.5, and then we did a second pass with GPT-4. In our second pass, we also attempted to do some of the cleaning we'd previously done manually as a second step to our prompt. So, reformat this as a list, separated by commas, remove all the periods, just things that are going to make the data cleaning process easier. And that was actually, that saved us a lot of time. We found that GPT-4 was more reliable than GPT 3.5 and performed a bit closer to the recall we might expect to see as the difference between two human coders. Like two human coders are not necessarily going to identify exactly all of the same words as difficult for a middle schooler. So, we would expect a little bit of a difference that wouldn't be that far off from what we saw with GPT-4. The results also showed that both versions of GPT, false positives were more of a problem than false negatives. So they were more likely to identify, GPT was more likely to be more liberally consider a word to be difficult for a middle schooler than a human coder was. So when we inspect these false positives, we find that they break down into four main categories across two dimensions: whether the words have a mathematical definition and whether the words are challenging vocabulary. So thinking down the line about how this metadata might be used, a question with a high count for vocabulary might trigger a support meant to assist students in reading the problem, such as offering definitions, offering to read the question aloud, or offering an animation of the question scenario. Just support's meant to help kids who are struggling to read the question. When viewed this way, the vast majority of the words are either math words or challenging vocabulary. So only 50 out of the 273 false positives are neither. So if the GPT tags result in a question being accompanied by a support when the human tags do not, the consequences of false positives seem minimal and maybe even beneficial. So thus we are paying more attention to the recall result, which gives us confidence that we can use LLMs to generate our assessment metadata in the future. We learned a lot while we were playing with this. So if you are hoping to apply this technology to your own assessment items, we have a few recommendations. You should set creativity to precise and max response size to short, and then also specify the format for output. So if you want it as a list separated by commas, tell it that. You have to tell GPT not to answer the question because it naturally wants to answer the math question instead of just generating the metadata. And you need to go through a manual cleaning process afterwards to remove your predictable errors. It will use words from the prompt in the output and things like that. And also using a multi-step prompt was a way for us to sort of, when our prompt engineering wasn't giving us the output that we wanted, just making it a two-step process where we then have a second column that sort of cleans the first column that solved a lot of our problems. We're doing some other things with AI at OpenStax in the K-12 space. And right now we have this exploration around teacher-facing tools that AI could potentially help with. This is nascent early stages. And we're sort of comparing an AI solution to a more low-tech solution to see if AI is really actually adding anything to this conversation or if we're just using a hammer because it's there. But if you want to know more about this, I'd be happy to talk about this via chat in the Whova app. And then hopefully another thing that we're doing with AI is hopefully we'll be able to test Candace's alternate word problems to see if they are effectively increasing student motivation and engagement and increasing student learning outcomes. So, we'll hopefully be able to actually apply Candace's alternate word problem idea in real classrooms and see if they're having an effect on learning sometime next year. And that is it for me. Are there any questions?
All right. Well, if any questions come up, feel free to follow up with any of the three panelists. We'd love to talk to you more. And thank you all so much for coming to our session.